So do we have permission to start? If you can all settle down, then we will begin with the third session of the day, Challenges and Prospects for Quantum Technology Development. In this session, we will delve into the exciting field of quantum technology, exploring the challenges and the various initiatives taken by Department of Telecom, CDAC, TEC, and also in UK and Switzerland, in supporting the growth of quantum technology and enabling standardization and market access. It's now my honor to invite on stage the chair of the session, Shri Kishore Babu, DDG, SRI Division, DOT. Shri Kishore Babu is requested to kindly join us on stage. He's chairing the session. And our learned panel consists of Shri Nagendra Nagaraj, CEO of QpiAI. Please welcome. Shri Abdul Kayum, Deputy Director General, 6G TEC. He'll be joining us. Dr. Bruno Huttner, Director from ID Quantique, Geneva, Switzerland. Welcome, Dr. Huttner. And joining us online will be Timothy P. Spiller. That will be later on. So without any further ado, we will begin with the special address by Honorable Chair, Shri Kishore Babu, DDG, SRI Division, DOT. In his current role, he facilitates engagement with Indian digital communication technology companies in the domains of standardization, R&D, innovation, to drive the Government of India's technology policy objectives. He has over 28 years of experience in diverse leadership positions in information and communication technologies and telecommunications. Shri Kishore Babu has made important contributions in ITU and APT by holding various positions there and is also the Vice Chair of Council Working Group Internet at ITU. I request Shri Kishore Babu to kindly present his special address.
Very good afternoon to all of you. Next slide, please. You all have heard about the National Mission on Quantum Technologies and Applications, and under which quantum communication is one of the pillars or vertical, where Department of Telecommunication is driving engagement with industry, academia, and as well as global stakeholders. Last year, around January 2022, Secretary Telecom constituted an interministerial committee or interministerial task force to bring stakeholders, especially the industry, academia, together about what we should do and what are the areas of interest and what are the challenges we should address, especially to bring a kind of engagement as well as collaboration among the stakeholders. You can see on the screen, the interministerial committee or interministerial task force consisted of the various departments and industry and academia members, including TSDSI and our members from CDOT and others. So together, they came out with a comprehensive analysis and report with regard to quantum communications, which happens to be one of the pillars of the quantum technologies and applications. This IMC report almost took around 9 months, where we had, what I should say, tens of meetings. In turn, we also formed some of the task forces within to work on various aspects of quantum communications. We can see many of the members who contributed significantly for this report are also present here. And the key agencies or key organizations which contributed to this, you can see on the left extreme. It includes industry members. Of course, more than 8 to 10 industry members contributed. And we have got Office of PSA. I think I saw, Madam Preeti here some time back. ISRO, Academia, CDAC, PRL, RRI, NSCS, DST, DRDO, DOT, and our R&D organization CDOT together contributed for this report. And one good thing about this report is having done a kind of detailed search with regard to who are all working in this particular domain, what agencies, what industry members, which research institutes working on the program, especially quantum communications part. First and foremost, we did something called to identify where we are. What are the current competencies in terms of the ongoing research work, in terms of the products what are under development, what are all the highly evolved products. This a list has been prepared, which includes what are all the indigenous competencies in both industry as well as academia. And then it also looked at research activities happening with the support from MAIT as well as DST, which are already began in different institutions that also have been catalogued. And importantly, we realized that in any R&D funding, the key aspect goes into buying the equipment and buying the instruments. We also catalogued what are all the different quantum communication R&D infrastructure which have been established through various funding schemes of departments. That list and equipment also has been catalogued so that it is available as a federated R&D infrastructure for one and all for use. And of course, we also identified a big list of experts. And importantly, we also looked at when these experts, these research projects, when they go on contributing, excuse me. So we realized that there's a lot of opportunity for standardization, especially in various standards platforms, namely IEEE, 3GPP, ITU, other institutions, including NIST, where they're significantly working on various standards. Even these standardization opportunities and gaps have also been listed. And most importantly, the policy recommendations and the macro level roadmap. All these things brought together in this particular interministerial committee report, which would be made available very soon. And as I mentioned, this also comes with an annexure of products which are all available above TRL level 4 and above. What could be available in terms of quantum key distribution, PQC, QRNG, even these are reflected in this particular interministerial committee report. Next slide. And this is the constitution of the committee, which is chaired by Member Technology, Digital Communication Commission. And these are all the different members and representing various institutions who contributed for this program. And you can see the institutions which are from research background, industry members, TSDSA, Standard Development Organization, as well as our CDOT, TEC and others. They have been part of this engagement. Next slide. I mentioned about some of the task forces which has been constituted under the IMC to make the, what's called a detailed report. These are the kind of task forces which have been constituted, which worked in detail about this. You can look at almost like 30 plus institutions are working on the quantum communication technologies. We wanted to look at what kind of synergies, what kind of collaboration is possible among them, because collaboration is the key, as you heard from the previous speakers as well. Here we are to understand about what is happening where, what way we can work together. So one task force worked on this building synergies across institutions. You can see here under the champions, Madam Urzi Shinha, Mr. Pankaj Dilela and Dr. R.P. Singh, they contributed for this. And similarly, identifying the use cases, applications and enabling pilot trials. We have got a list of champions from industry, including from Nagendra to Mr. Rahil Patel. They all contributed to this. And facilitating IPR creation, which a part of bigger objective overall to facilitate communication IPRs in India. So there was a stream on that as well from industry. And standard development opportunities and to coordinate India's unified position on the standard platforms, that also becomes part of this report. Policy measures to promote QC products and production and deployment. This is one of the key areas. Having seen there are already some products coming in the market which are already above TRL 6 and above. In one of the presentations which was made to Honorable Minister, the clear direction and mandate is that yes, wherever there are products available, respective ministries and vertical, they should give opportunity for doing the pilots. I'm happy to see that some of the pilots are already in progress in NIC as well as some of the agencies of railways. The last part is about evolving a kind of clear action plan to promote ongoing efforts as well as to give opportunity for pilots on the existing products as well as solutions. Next slide. This is a kind of macro level roadmap uh, proposed from the key members of the task force, which looked at ongoing efforts, which looked at the collaboration, what is happening between India and as well as other institutions, and also the kind of opportunity where India can build bridges in reaching some of the research objectives. You can see starting from current QKD demonstration, which almost crossed 150 kilometers. We are also looking at integrated photonic chipsets sometime between 24 or 25 plus, and also satellite-based QKD sometime around 25, 26. Altogether, they form part of the roadmap which is being worked upon, the 2047 Vision India roadmap. They, what meaningfully fit into that engagement. Next slide. These are some of the standardization opportunity which is happening right now in different international platforms. The report also codifies, a report also catalogs where all we are having opportunity to contribute on standards platforms, especially taking note of strong research activity ongoing as well as new work, new areas of research which is happening in India, which also puts India in one of the few countries about new research areas going on in quantum front. Next slide. Next slide, please. So unanimously, the topmost recommendation is about to draw a national level program for quantum communication, especially for giving opportunity for pilots in different economic verticals wherever there's an opportunity and need for building what's called secure communication among different communication entities, and enable establishing public testbeds in quantum communications in partnership with industry and academia, and of course including and integrating quantum security is one of the key priority in all the strategic verticals and the strategic sectors. Next slide. Test and certification is one of the important areas. As we see the evolving products, we also want to be clear about these products and solutions meet really the required conditions, required criteria, which is evolving in different standards platforms. That of course, whatever developed meets our requirement, giving a sense of confidence to the users, and making available quantum communication public R&D infrastructure. As I mentioned to you earlier, we have also catalogued all the infrastructure made available through different R&D schemes. The opportunity is about how this infrastructure could be made available to different industry members as well as other academic institutions who are to make use of this infrastructure, and opportunity to create a kind of interministerial subcommittee to work on funding of R&D projects. You may be aware that Department of Telecom has come out with two schemes. One is called DCIS scheme, one more is a TTDF scheme. Both are available on DOT portal. The first window of opportunity for TTDF was opened sometime in December 2022. Next opportunity would be also opened very soon. And we have seen a lot of quantum projects have applied for funding need in the first window, which are still under evaluation. Next slide. And TEC is going to play a very important role in driving this engagement in partnership with CDOT as well as TSDSI, both research as well as standardization activities. So as a facilitation center, they will be available to create collaboration opportunities, enabling pilots in this particular important domain. And especially this application use case labs, where all we can use this quantum technologies and applications in strategic verticals. This is one of the need of the hour to build awareness as well as to make use case pilots as well as adoption opportunities. So with this, thank you very much. We look forward to hear more from the other distinguished members.
Thank you so much, sir, for throwing light on DOT initiatives on quantum technologies. Our next speaker is Dr. Nagendra Nagaraja. He's the founder, CEO, and chairman of QpiAI. He has done his PhD in wireless, ML and AI from Coventry University, UK, and master's from Illinois Institute of Technology. He has over 20 years of industry experience in semiconductor electronics, wireless systems, and artificial intelligence. Dr. Nagaraja has 30 granted patents and many patents under review in the areas of AI and ML, security, wireless and multimedia, and quantum technologies. I request him to present his keynote address.
Thanks for the opportunity. Thanks for chairing respected Kishore. So today we are talking about in this keynote challenges in quantum compute. Quantum compute is pinnacle of all the computation what humanity knows. Okay, so obviously there will be a lot of challenges, both implementation, integration, as well as making it scalable. Okay, so I'm going to touch some of those challenges that the way we worked on as a company. We have come a long way. We have created a lot of IPs. We have taped out multiple chips. Okay, so we are building a full stack quantum computer in India. So one of the most powerful one. So what we learned along 3 years of development, I'm going to share on this. And before I start challenges in quantum, let me tell that quantum and AI will be inseparable. If you want to have a fantastic quantum system, you do require AI to help there, and future of AI is quantum. Okay, so yeah, so basically what we have is we're building a 25 qubit system which is scalable to 300 qubits. Okay, so this is our own chip and our own controller. We have built room temperature control for this, and we have built complete software stack which is tested with multiple large enterprises which are big pharmas, banks, and then chemical company, and then financial institutions, and as well as we have enterprises in the industries. Okay, so what our vision is, quantum computing should not be just at scientific institutes or university, but we are taking it to enterprise. That means every big organization should have access to quantum computing, either through cloud, through what we call it as quantum computer as a service, or on-prem installation of quantum computers. Okay, so basically on this way we have filed around 10 patents and one is granted, and we also built multiple stacks to enable this quantum computing. And I will go through both hardware and software challenges along with the system challenges that we faced. Okay, this is my team. We have around close to around 12 PhDs in our team. Okay, most of them are postdocs and PhD in quantum computing, microelectronics, theoretical research, AI, and other similar areas. Okay, so QpiAI is part of QpiAI Technology, which is a parent company, and we have around 40 engineers, and then 13 of them are PhDs, and then we have a Marquee Advisory Board, which is very good at, which has a very good accomplishment in quantum computing and microelectronics, these two areas. So basically, what we're trying to do is we're trying to provide an integrated solution for deploying quantum technology. It's not only building quantum computer, but actually deploying quantum technology in enterprises. Okay. So the way this entire system work is it has to come from a business problem. Okay, so we need to identify business problem in various vertical. It can be healthcare, it can be banking sector, it can be logistics, automotives, and even in finance. Okay, and what we have designed is there are 4 parts of any solutions here. One is QpiAI Pro, which is an AI based modeling platform. It's a classical AI. But then when we combine with QpiAI ML, which is a quantum machine learning, it actually combines both classical and quantum machine learning. And we have an optimization solver. Basically, it is solving the icing problem, and it maps combinatorial optimization problem, which is a very hard to solve optimization problem. This problem occurs not only logistics but also in drug discovery, material discovery, and similar hard to solve, hard to solve multi-objective optimization problems. And we have a sim where we have to do a quantum simulator because obviously number of qubits is not good enough. So we have a quantum simulation libraries. So with these three, I think we can map it to current GPU or ASIC, and whenever the quantum comes, we have 300 to 400 qubits. We just flip the switch and we have all our software running on quantum computer. So this is a really enterprise-grade solution with an integrated approach to AI and quantum, where our customers can really start deploying quantum today. So some of the impact quantum computing will have on the various industries are logistics, energy, and then financial services, automotive, healthcare, and drug discovery, chemical discovery, aerospace. Okay. So currently, when we talk about deployment of quantum computer, basically a company which want to deploy or the customer who want to deploy it faces a chicken and egg problem, because until we have a number of qubits increased, we will not be able to have commercial grade quantum computing. But then, most of the customers are willing to actually take the software out, where at least they make sure that their key projects are covered on the software, and they're okay to procure this 25, 30 qubit machine, so that at least their engineers are ready for quantum computing. So that's where we are today. And basically, the arrival of quantum computing will impact almost all vertical industries, as we know of. Okay. And this is our approach. Basically, what we have is we have this libraries where it will be given as APIs to the programmers, and we have a simulator which is inbuilt, okay, which converts this the libraries into gates, and that will go on the hardware. So basically, what we have is on the hardware layers, we have a simulator, which is a QpiAI Explorer, which can do 20 qubit simulation. And we have a controller which can, which is indigenously designed. It's a 16-channel controller for controlling the qubits, both spin and superconducting qubit. And this is already there. This is in the production. It's already at TR11.9. We are sampling with some of the customers. And then we have a Creo IC which can bypass the room temperature control, and which can get integrated into cryogenic fridge, where it directly talks to quantum computer. And this chip is getting taped out in August timeframe. So with all these things, what we have is a full stack solution where customer can integrate either through simulator or real quantum computer, and start actually road mapping their technology for the enterprises. So this is a 25 qubit machine that we are working on, and it should be launched by Q3 of 2023, not 2024, 2023, and Q1 2024. This is scalable until 300 qubits. There is absolutely no change in software, no change in existing infrastructure. The last layer of the cryogenic, that is our qubit chip, okay? So only those keep on changing. Our control is all extensible to 300 qubits, okay? And even the infrastructure support 300 qubits. So once this is deployed, I think the change will be, the progress will be rapid, okay? From 25 qubit initially to all the way to 300 qubits, we don't expect it to take more than a year. Okay, that means to say that we are planning to deploy 25 qubit machine in our premises and our customer premises by end of this year. Most likely by 2024 end or early 2025, we should have 300 qubit machine. That is commercially a viable quantum computer for at least in molecular discovery and drug discovery. 300 qubits is good enough if they are not noisy. Okay. So this is how the full stack quantum computer look. Basically, you have a cloud service application layer, and then you have a circuit compiler, which is developed by us. And then we have a control layer, which is co-located near the server. Wherever the server is, the control layer, quantum control layer will be there. And then we have a cryogenic environment to, really operate on the qubits. And alongside this is two different domains. One is a digital domain, which is a cloud-based infrastructure application layer. And the control and actual hardware is all RF and analog. So this is where the challenges comes, because The RF and analog, what we're talking about, has to work at 4 Kelvin or below that 10 millikelvin. So that is where the challenges comes, and it has to interface with the real world applications. So what is the challenges in the application layer? So the kind of application we run on the quantum computers are like typically like optimization problems, and then the machine learning in finance, and then material discovery. So all these things will be running on the cloud, okay, or in your on-prem data center. So now this has to be translated, and you need to generate quantum circuits and quantum system using quantum circuit compiler, okay, and then it has to get executed on a co-located server. So you see this is we are talking about two different kind of environment, because this is extremely cold cryogenic environment where the servers are, and then your application is running at maybe at 30, 40, 50 degrees centigrade. And this may be located somewhere else, okay? And we have to understand that again, controlling these qubits, which has a decoherence time of few microseconds, right, currently, okay? Even if you take the best of best qubits, their decoherence time is T1, T2 time will be around a few microseconds, and that will become challenging when we actually deploy it in the cloud. So these are the practical things we have faced when we started deploying certain applications on the real quantum computer. We have deployed many applications on real quantum computer. Of course, we use Bracket, and we will have our own quantum computer soon. But these are the practical challenges we faced. One of the things is SDK. You have to develop a standard SDK for quantum algorithms and quantum software developer, and then the cloud application for managed jobs. So it's not easy just to let job run, and the jobs has to be managed because each of this will take many days together to complete. And challenges there is if it is incomplete and it doesn't complete all the iteration, then entire job is wasted, and it's very costly. To let you know, we did a molecular discovery on this, molecular discovery using Bracket, and one iteration of just energy calculation would cost us 200K. Okay, so that's a challenge here in managing things. This is a very costly job, and we have to manage them very well. Otherwise, the cost will run in millions of dollars in doing any experiments. And the computation workload distribution between GPU and quantum computer. So we're coming up with a specialized chip for this. Currently, we don't have any solution. Suppose if you want to manage the workload, what has to go into GPU, what has to go into quantum computer, that has to be cleverly managed for optimal results. Otherwise, neither will get optimized compute, which is a distribution of hybrid quantum and classical. Neither workloads will be able to complete faster. That means your end results will not be optimal. So now coming to quantum circuit compiler, what are the challenges? Now the thing is, we have an intermediate representation called QASM, okay, which is a quantum assembly. And what happens here is it's not standardized. Okay, if somebody is using an interface to our own simulator here, so we are going to provide our own format here, right? So that means to say that for ecosystem to develop, we need to have a standardized QASM, something like x86 or ARM. So we don't have any standardization in the assembly. So that has to be done for really having a thriving software ecosystem. And then development of hardware over optimized simulator compiler. Okay, so currently, if you look at what IBM has, it's very much tied to their quantum computer, and we don't have a compiler like LLVM or other open source compiler CLang that we have available for all the compute. We don't have something like that, and that creates a lot of when we did a large scale program, okay, which has really huge circuits. So this was always a problem. It used to work on certain quantum computers, and it never used to work on certain other things. Okay, and then the framework for hybrid quantum classical compilation. So we formed our own framework. It works well with our own quantum computer. But then if I want to make an open framework for this, say we want to create some kind of an open source, so where many application developer can develop this. So that is a challenging thing, because there are 4 different players, and each will have their own kind of method. And when the developer actually start developing for 4 different applications, it will be very hard. So ecosystem is still very nascent when it comes to quantum circuit compilers and other things. Okay. And then control layer. This is very important because now we are until now we are dealing with all digital. Okay, so now we are dealing with control software where pulses are generated. Okay, RF pulses, and it has to control the real quantum computer. So there are two parts here. One is the room temperature control. Of course, there will be a lot of wires here. We are doing one project where we reduce this wire and we build a control circuit which is integrated into fridge. So here the problem again is like the latency of a control. See, most of this, the room temperature control will come up with latency of 200 nanoseconds. That's really long for any closed loop control that we can do. So we have reduced it to around 100 nanoseconds. Even that is not enough. And most of this, if I go for a spin qubits, it has to be controlled by AI, because you have to do a lot of calibration in order to make a spin qubit work. Superconducting is still much more stable, but for spin qubits you do require machine learning libraries. So there you cannot have acceleration of machine learning out of this box. That means you have to integrate AI chip which is on the host. Okay, so in order to reduce latency. So the entire circuit compilation to actually feeding on to control software and generating pulses is the hardest path in the quantum computing. Okay, apart from building qubits, this is a day-to-day operation, or maybe like every nanosecond operation that goes on here is extremely complex compared to any other compute, because there is a variation. This is a very this is a very high speed signals what we're talking about. This is not like in gigahertz, 2 or 3 gigahertz. It's much higher than that, maybe in 10 gigahertz, 20 gigahertz kind of thing. And these pulses has to be generated by the software, okay, which has to translate and generate the controls for this. And this is one of the things which is very challenging when we practically implement quantum computer. And coming to the last one, that is the physical layer. Okay, so in physical layer, what happens? The cryogenic environment. Again, a lot of things can affect this because it's a very delicate piece of a hardware. Okay, so decoherence time will be in microsecond. We hope that one day we can see in milliseconds. Here the problem is EMI and EMC and the radiations that can affect the qubit itself. So in our office we have formed a shield. Okay, so we are bringing a qubit, so we formed a shield there. So where we isolate from all kind of noise, and that shielding itself was very advanced. I mean, very detailed work that we have to do it on the lab. Okay, and on the operation side, again, we can't place this fridge on 11th floor. Okay, there will be a structural vibration in the building that that can affect the qubit operations very much. So we can also do that in Japan. I think only one place where they put it at 7th floor is in Japan, where they actually drill the wall and took the fridge inside, not to the door. And there they put some dampeners and other things to actually compensate for vibration. So this is a very high precision work. Okay, you have to account for radiation, you have to account for vibration, and you need to account for any excess heat that that goes into the system. Okay, so the kind of engineering that goes on cryogenic and making this qubit work is really precise. I would say that this is one of the most advanced engineering that is required to make quantum computing work. Okay, and in here again, what we have is we have a cryostat, which is a fridge. This is one of the costliest thing of all the components. The chips we manufacture, of course, chip we have to actually the qubit chip and the control chip and the hardware all ready. Okay, but this fridge, when we bring it in actually, and the way we place it, currently it is consuming for us, the estimation is around 80 kVA. That's the power it consumes. Okay, and if I need to operate 2 qubits, I mean 2 qubit chips, we can do that in a fridge. The power goes up. Okay, and we have to actually make sure that the power is completely uninterrupted. The power lines are noise free. Okay, if there is a noise in the power, then the qubit will not work. So basically, what we're dealing with is it's a very delicate part of a nature that is given for us for a computation, and to engineer and make it work is extremely challenging. Okay. So now I just move to, we are developing one more chip on quantum communication that is already ready. Chip is taped out. We are just assembling and we will be supplying it to first customer, maybe Dot and maybe another few QKD companies here. So here again, we have to cool it down to 2 Kelvin, 2 or 3 Kelvin, and only one company which has that kind of cooler, that is in Japan. Okay, so to build this cryostat, we could do it manually, but still that compressor is coming from Japan. Okay, only one company in the world which can cool it down to 2 Kelvin. And that is another thing that is very challenging. We are also working on HTS, high temperature, single photon detector. That should also miniaturize, quantum computer, this communication chip, and also we can have a TC at around 70 Kelvin. Okay, so that is getting fabricated in ISC. So we're using a lot of research to get this done. And here the challenges is noise and the way the signal loss is in the transmission. Okay, so the reason why we require SNSPD is the range of QKD system. Okay, if you really want a very secure, high efficiency system, you can have efficiency. Most of the efficiency I know, which can be obtained at room temperature, is 30% or maybe like 40%. But if I need to go to 90% efficiency, this chip is very much required, and we are forming this single photon detector here. And challenges obviously is noise isolation and how do we reduce signal loss transmission. And some of the medical applications, we are also using array of SNSPDs for X-rays and other things. And then we have a problem with limited distance in transmission. We are yet to come up with repeaters or quantum memory. So that is our next chip. Once this is taped out and this is deployed, we'll come up with a quantum memory so that the range is extended beyond single photon detectors. And this is the holy grail of all the things what we are doing, where we really want to make sure that the quantum secure communication between two quantum computers. Okay, so basically it's all quantum here. Like computation is quantum, communication is quantum, and this is like connecting one of the most powerful computation units through a secure communication channel. Okay, and here again the challenges are the same. It's a double the challenge, communication challenge as well as a compute challenge, and solving this would give us the leapfrogging to the next era of whatever we know in the technology. Okay, a lot of things are possible when we do this. Not only we can do a better vertical processing of banking or material sciences or chemicals, and also we can have a very secure communication. The first industry that's going to affect from quantum security is the banks. Okay, so that's about it. Thank you.
Providing quantum solutions to various industries across sectors, the CEO of QpiAI. Dr. Nagaraja also talked about various challenges in various layers. Thank you so much for your keynote address. And joining us virtually now is Professor Timothy Spiller. He's the Director of Quantum Communications Hub and also founding Director of the York Center for Quantum Technologies, University of York. Before this, he was at the University of Leeds in the roles of Head of the Quantum Information Group and Director of Research for the School of Physics and Astronomy. He has spent over 40 years researching quantum theory, superconducting systems, and quantum hardware and technologies. He is an inventor of 25 patents linked to quantum technologies and applications. He'll be giving us the perspective from the point of view of United Kingdom. He'll be talking about the UK National Quantum Technologies Program. Can we have him here on screen, please? Professor Timothy Spiller. Is he online with us? Sir, can you please share your backdrop with us? Professor Spiller. So as you can see that your presentation has been already uploaded, and then you'll be able to change your slides from there itself. Can you hear us? Professor Spiller, can you hear us? You'll have to unmute yourself. Can we ask our next speaker to make his presentation in the meantime? Bear with us kindly, we're just trying to connect to him. Moving now. Earlier it was static. I said at least he's moving now. Yeah.
Can you hear me now?
Yes, we can hear you.
Excellent. Okay.
So, as you can see, we have uploaded, sir, your presentation. You can change your slides from there itself. And you may now begin. Thank you.
Apologies for that. We did a test last week. Okay, I'm here to tell you about the UK National Quantum Technologies Programme very briefly, and then the work that I lead in part of that, which is the quantum communication side. So thank you very much for the opportunity to talk. So the UK National Quantum Technologies Programme was established in 2013. It began in late 2014, and it ran firstly for a 5-year period through to 2019, and then it was renewed subsequently for the second phase that is in at the minute, which is 2019 to 2024. The estimate of the total budget that will have been invested in the 10-year period is about £1 billion, so that's about £100 million average. And that comprises the UK government contribution, the contributions from industry, and the contributions from investors investing into quantum-related startups and the like in the UK. So it's quite a substantial investment. And the main focus from the academic-led perspective for part of the UK national programme, the part that I'm involved in, is focused on 4 large quantum technology R&D hubs. And those hubs are designed to cover the whole spectrum of quantum technologies. So there's the hub in sensors and timing, led by the University of Birmingham. There's one in imaging, Quantique, led by the University of Glasgow. There's the computing and simulation hub, led by the University of Oxford. And then there's the quantum communications hub that I lead from the University of York. So these 4 hubs cover essentially the whole spectrum of quantum technologies. And in addition, in the quantum computing domain in the UK, we are now establishing a national quantum computing centre, which, if you like, forms a tech transfer route for the computing and simulation hubs. So that will be a physical building built on the Harvard campus just outside Oxford. Whereas the hubs are all delocalised large collaborations, and I will show you a slide later that contains all that components. So, in terms of what we're focusing on in the quantum communications arena, then certainly in the first 10 years of the UK national programme, our focus has been on quantum communication for quantum security. So we've had a very strong security focus. Clearly that can diverge over time, and we expect it to in the next phase, which I will mention right at the very end, when there will be a kind of more of a merger between quantum communications and distributed quantum computers on the line. So, in terms of the security issue, I think you're all familiar with this. I will skip over it because I think that Kelly Moscow is actually talking later. But it's well known that quantum computers will render some current cryptography, in particular RSA and current elliptic vulnerable in the future through Peter Shor's algorithm, which was not being known. And of course, as has been elegantly pointed out by Kelly Moscow, in fact, although a large quantum computer capable of breaking RSA doesn't yet exist, if the security shelf life of your data that you're sending around at the moment is encrypted, if that security shelf life is very long, then you probably should be concerned now, because of course it may well be that people can intercept encrypted stuff now and decode it later. And so if you have long security shelf life, you should be concerned about that now, not just when quantum computer appears. Now, there are basically 2 approaches that are being developed, taking forward, if you like, security against the threat of a quantum computer. And those 2 directions are quantum communications technologies, which we'll get further to, but also new mathematical post-quantum cryptography is being developed, notably through the NIST process run by NIST in the US. And I think the perspective that we have, certainly in the UK national programme and in their hub, is that both of these 2 technologies, quantum communications, but also new mathematical crypto, should be combined to maximise the security in a future quantum-enabled world. Now, our work we see, security is clearly, somewhat sector agnostic, and it's relevant in very many sectors. So we consider our work to be relevant to defence, for finance, for ICT in general, in space, in finance industry, in medical applications. And so I think security underpins essentially all aspects of life in general, when public and personal life, commercial or government applications. And so we see security as being rather ubiquitous. But I think the important point to note is that security requirements may well vary from sector to sector, from individual to company to government and so on. in that case, the actual solutions that get delivered into those sectors may well vary, and they may well have different constraints and different concerns about the level of security that's acceptable. And one particular physical constraint that's actually quite an obvious one, but very important, is size, weight, and power. So clearly, there are applications in various sectors and in various technology applications where swap would be extremely important. So you might want very compact and rather low energy consuming security hardware, and that might be with small handheld devices, that might be with going in small or rather compact satellites and so on. And of course, there may well also be some sector-specific solutions. So there may well be specific applications, for example, relevant to finance and banking and other sectors. And I will stress, and I think this was mentioned in an earlier talk, and I'll come back to it very briefly as well, that standards and assurance are very important across all sectors. You need to know that the technology is doing what it says. Now, most of the work that we've done in the quantum communications hub in the first 8 years going on towards 10 years of the two phases of the UK National Programme has focused on quantum key distribution, because that is essentially the most advanced tool of quantum communication in terms of where it's progressed towards technology. Indeed, we can clearly buy various forms of quantum key distribution technology from various vendors worldwide. So that's advanced quite significantly, and that's the main thing that we focused on, although I will mention very, very briefly one or two others in a few slides' time. But the important thing about quantum key distribution is that the quantum particle of quantum key distribution is the distribution of the key by quantum units. And that key, once quantum signals have been distributed and the key has been distilled from those, then that key can be used in multiple conventional applications, whether it's printing data, or whether it's getting through a building, or whether it's a password, or whatever. And there are many applications, of quantum keys, but the quantum part is the distribution of those keys. And of course, in general, in security, keys are consumable items, and so once you use them, you should delete them and not reuse them. And so you have to top up keys every so often, and that top up is also a quantum aspect of the technology. One important point to note, and this is one place where post-quantum mathematical crypto and quantum technology may well work together very well, is that quantum key distribution requires authentication, and that's to appreciate the key on some other means, and certainly in terms of dynamic networking where users come and go, it's probably not really scalable to use brief-down key between devices. So something like a PQC authentication mechanism would work very well with QKD systems. So that's something to keep in mind. Now, at the minute, because we sought to provide, as I said, security technology applications across all sectors, then our approach in our hub at the minute is to actually consider quantum secure communications at all distance scales. So I'm going to start with a quick dive at very smallest distances, so between a handheld device and either another handheld device or some device or something, then clearly flexibility would mean that you would want to do things over from space. Then you only need to cover the distances. And in the hub, actually, even started in 2014, we worked on very small devices, at least on the transmitter side, that could actually fit in a mobile phone in the future. So you could have the ARIS transmitter in a phone, and you could have some kind of receiver in the phone. So we call that consumer QKD. We've developed that now to the point where we see that as a tech transfer. And I think it's worth noting, I mentioned already, that low flock is clearly very important for at least the transmitter side, if that's what it's in a handheld device. And for putting stuff on the chip is clearly very desirable. And it was very pleasing to know that even during phase one of the hub, that's been one of our hub partners, the University of Bristol, with forward and testing now a growing company with chip-based quantum communication devices. If we go up distance scale from the smallest, which is free space, and when you go to intermediate distances, then somewhere like the UK has a pretty good and well-established fibre network quantum communications over intermediate distances. And indeed, during phase one of the hub, we established the UK's first quantum network, which comprises a small quantum network around Cambridge, a small one around Bristol, a connection from Cambridge to British Telecom's R&D headquarters at the National Park near Ipswich, and we're borrowing the mix of the National Dark Fibre facility with the river networks in Cambridge and in Bristol. So we operate with QKD for quantum networks and over the UK quantum network. And it's been very good to see that that work has already transferred. So, first of all, another aspect of the UK national programme is those of technology hubs are significant industry-led projects funded by Innovate UK, and much of our work on fibre-based quantum networking transfers first into industry-led projects that were funded by Innovate UK as part of the UK national programme. But even further than that, now British Telecom and Geneva have now got a trial commercial network operating trusted node QKD in the City of London with EY for trial customers. So it's been very good to see that work evolve from the Tesla R&D network through to industry-led projects through now to genuine commercial trials. And another interesting point to note is that we've worked with other fibre networks, and at the moment we're pursuing with Network Rail in the UK the use of trackside fibre for QKD signals, because most railways in the UK have optical fibre running alongside it. So there's a very substantial network that's operated by Network Rail. So that's intermediate distances. If we go up yet again in distance scale, then having gone from free space and short distance to fibre-based and intermediate distances, we go back to free space at worldwide distances. Maybe if you want to get beyond wide report. Then the use of satellite signals either from or to satellite quantum signals is the way to go in order to connect places on opposite sides of the world with quantum communications, because as we know, undersea fibres that contain built-in amplification cannot support quantum signals. So even if you can go in rather long distance operation, you've still got to with range. We expect quantum repeaters and memories and things to develop further in the future, but at the minute, the way to get the longest distance is through satellite links. And indeed, in the UK, there's quite a significant activity in our hub. We will be launching next year a small compact to test satellite around QKD, and we'll have lots of ground stations operating at Aerodrome in Scotland, near Harriet-Watt University, one of our partners. But there are other missions going up as well from the UK. There's the ROCKS mission led by Crash Prospect, and FEC visits with UK Singapore mission will also be launched. So there's significant UK activity in CubeSat investigations into satellite communications. And of course we know the Chinese have done some fantastic experiments already demonstrating that at least in principle this is possible with their missions, satellite resorts a few years back then. There are other worldwide projects going on that we hope to collaborate with, such as the Canadian TEC mission. They will also be launching satellite ongoing. So that kind of covers the whole spectrum of the work that we're undertaking in the hub at the minute. I would just like to point out now very briefly that we do have other activities going on in our hub, which are not just QKD focused. So let me just mention a few of those. The first one is that we have significant work now going on in developing specific sources and detectors for quantum communications. So if you like, we're hoping to grow the supply chain that exists to support quantum communications and indeed quantum sensing and other aspects of use photonic sources and connectors and detectors in the UK. So we're developing sources and detectors. We're also developing and working on quite a number of new protocols besides just conventional QKD, so things to do with signatures, but also things to do with quantum protocols. Bring in also the constraint about the finite speed of light time, bring in special relativity as well as the irreversibility of quantum measurements underpin them. So there are plenty of other protocols in the pipeline that are more at the R&D stage at the minute, but in the end, is very much the keeper of quantum standards, and they do a great deal of work on that. So we've traditionally been contributing to XE over quite a number of years, as XE was one of the pioneering standards bodies with quantum key distribution standards work that's been going on for many years at XE, but now I think many other standards bodies worldwide are picking up on that. So we're well integrated into contributing to quantum standards. And we're also looking at combining PQC and QKD, so we're well aware of the outcomes of this process. We have our partners that actually work to combine these two technologies together. We've worked on random numbers, so in phase 1 we developed assurance methods for device-dependent random number generators, quantum random number generators, and that's transferred now to a large Innovate UK project as part of the national programme led by NPL, containing many vendors. And so at the minute, the random number generators that you can buy are device dependent, so you have to devise bespoke tests in order to assure that they are indeed working in quantum way, whereas in the future, of course, independent. Well, not only random number generators, but quantum communications technologies as well, where you can effectively assure the devices by measuring the outputs and confirming the violation of the value quality and something like that. So then the tests become device independent rather than remain device dependent. So we've done significant work on that. And in terms of technology assurance, it's interesting to know that the National Science Security Centre has actually, if you like, changed the way in which they do technology assurance. So they now got the principles of technologies that so we're currently studying those with respect to their implications for, in particular, quantum security. Finally, just to show you, every hub in the UK will show you a slide like this of all of their partners. So, typically a hub is of 10 or more universities distributed across the UK, companies, national laboratories, and so on. So, this is the slide of all our collaborators during phase 1 and phase 2 that comprise the quantum communications hub. And so I'd like to thank all of them who have all contributed to the work that we've presented. My final slide is just to give people a few links if they want to follow up. And in particular, I would note that a couple of weeks back we had the budget in the UK where the future finances of the UK are announced by the Chancellor of the Exchequer. We had very good news in the quantum world in that there was a sizable, very sizable commitment of £2.5 billion to be spent in the quantum technology arena for the next 10 years, starting at the end of next year, at the end of 2024. And in conjunction with that commitment of funding, the latest version of the UK National Quantum Strategy was published by the UK government, so you can find it on the UK government website, which basically says what they wish to do at a high level over the next 10 years of research. So with that, I'll close. Thank you very much.
Thank you, Professor Spiller, for taking out time for our conclave, and have a good night. Thank you so much. Really appreciate. And now our next keynote speaker is Mr. Abdul Kayum, DDG 6G at TEC. He is an Indian Telecom Service Officer of 1992 batch, leading the standardization activities on quantum technologies in Telecommunication Engineering Center, Department of Telecommunications. Under his leadership, TEC has released standards on quantum key distribution system and quantum safe cryptography systems. He is a member of task forces constituted on 6G and quantum communication technologies in Department of Telecommunications, and also chairs National Working Group 12, taking Indian contributions at the ITU. Shri Abdul Kayum ji.
Thank you. Good afternoon. Post-lunch session and quantum, I can see, but I thank the delegates, speakers, that they actually came. We were really very fearful, organizing a high decibel event where minister is available. And this was the first conclave, and we were really very fearful how many people will be coming. But what we saw that whatever number you find here inside the room, the same number were outside the, And actually we tried to make as less inconvenience as possible. We tried to call the people also, but many people did not respond. So actually this we could not really get the right number, how many people will be actually attending this event. So sorry for some inconvenience that you faced. Since the morning, it's very small. Okay, so since the morning you have heard many learned speakers talking about different technologies, isn't it? So, but what we find, there is not, a large adoption of these products. So, is it not required, or is there any other challenge to it? So I have, in the last 1 year, I have been traveling to many universities, research institutions, and manufacturing companies. So what I found that they are making a lot of efforts, but there is a lot of missing linkages. There is not hand holding right from, let's say, from research institutes, it should go to the industry, and from the industry, there should be adoption by the buyers. So what is that gap? Actually, that we, as our colleague Kishore, Babu explained, that in the last 1 year we had a lot of, brainstorming, that if we want to take a leadership position in quantum technology, then we should fill those dots. Next slide, please. So we found that there is a trust gap. One question when I was discussing with some buyers, they say whether the product is quantum. So it is a very difficult question. Who can answer this to a normal buyer? If let's say a bank institute, banking, they want to introduce QRNG, or they want to introduce QKD system or PQC. But it is really very difficult for them to distinguish it from any other electronic equipment. It looks similar, and you can't see the quantum. So we found that unless we do something to bridge this gap, the wide adoption will not take place. So that is why this is the first outreach program where you find people from research institution, from industry, from the buyer. You can see many delegates from defense, bank, telecom service provider, from all spectrum you will find here. It is, we thought that unless we all sit together and understand what we need and what should be each other's role so that a wide adoption of this technology can take place. So here we find that compliance and certification is the thing that can increase wide adoption of the technology. So taking cue from here, next slide please. Oh, nice. Yeah, so here at Telecom Engineering Center, what we do, we have external and internal stakeholders. We discuss with university, research institution, development centers, industry, government, and users, and try to find out what they want and what they have to offer. For example, university may be having, some new protocols. But if that protocol has to go into product, it has to get standardized. Unless that is standardized, wide adoption of those things will not take place. So, and whatever we understand from our internal stakeholder, that we take to the different external stakeholder, for example, ITU, IEEE, we contribute there whatever we learn from our internal stakeholders. In the process, as you can see, we took the first document, that is the national standard on quantum key distribution. This we got released by our Honorable Minister in October last year. And since then we are working on how to test against this standard. And during those process we realized that really we have a lot of knowledge gaps. What I'm trying to say, you have ITC standard, you have ITU standard, you have IEEE standards, but when it comes, how are we going to test on a product that is not written anywhere? So with the help of our industry, academia, we came out with the document that was released today, that is the test guide for quantum key distribution. Similarly, we are also getting input from the industry that we do not have any reliable national standard which we can follow for testing post-quantum cryptographic system. There are at least 23 companies in India who are having some kind of one of these products. But they when they were reaching to the customer, they were saying, okay, how do I believe on your product? So we came with the standards, and now you can see that this year we started testing with conformity assessment of products developed by QNU Lab and CDOT. Both are in the testing process. The CDOT product, that secured BC, we just tested recently. These are the national standards, international standard on, mostly they are on quantum key distribution. But everything is not covered. What I am mentioning here, it is a very few. If you see in any other communication area, you will find large number of standards. So these are the area where we find that there are no standards. So now I call upon the delegates to come forward, engage with Telecom Engineering Center, so that we take a lead in coming with new standards initially at national level, and then we can take it to the international level. Thank you very much.
Thank you, sir. And now I would request Dr. Bruno Huttner, who's here with us, to deliver his keynote address. He's Director of Strategic Quantum Initiatives at ID Quantique, Geneva, Switzerland. Dr. Huttner has extensive experience in the field of quantum technologies, particularly in the areas of quantum cryptography and quantum key distribution. He has authored numerous scientific publications on these topics and has presented his research at various international conferences and workshops. In addition, he is a co-chairman of the Quantum Safe Working Group organized by the Cloud Security Alliance, where he works to develop quantum safe security solutions for cloud computing and other applications. Dr. Bruno Huttner.
Thank you. Thank you for the invitation. I'm very happy to be here. I have to admit we didn't know that quantum was so active in India, and it was a great pleasure to see that. Not only a great pleasure, actually, we also saw many competitors. As you know, we are a company, so seeing so many competitors is not so good. But I think we are still at a stage where we are all happy to work together to build a market. So we are not at the point where the market is well defined and we have to fight so much. So I think what we need now is to define the standards to make sure we can work together to build the market, to find customers for QKD and quantum technology, quantum communication as a whole. And I think this conference is a good way forward to do that, and that's really why I'm happy to be here. So, how does it work? This way? Green. No, this one? Ah, green, yeah, okay. Yeah, with all, I'm colorblind, so for me green or the red is exactly the same. You heard a lot already about quantum key distribution, quantum networks, especially by previous speakers and by Tim Spiller as well. So I will simply give you our understanding of what is quantum communication, how we go from today's technology to tomorrow and so on. The first thing is we need to start from basics. And the basic is really that quantum technology is a new paradigm for information processing. So let me just spend a few minutes on this one because I think it's important to understand that. In classical computation, you are working with bits, zeros and one. And these bits are actually not something which are totally, there are physical things. And here I put a representation with this double well, and we put the bits as marbles into this well. So that's very simple. And basically what is strange is that a standard computer is only playing with that. You have many, many of these double wells, many marbles, and you can move marbles from one to the other. And if you do that, you realize you can do basically any kind of computing you're doing with a classical computer. There is nothing more than this to do classical computation. When we go to qubits, basically these bits are transformed into qubits, which are coherent superposition of these two zeros and one. So basically, instead of having a marble in one of the holes, you can have a marble which somehow is delocalized over the two holes, okay? And you can even build different coherent superpositions of these marbles. And here I put two of them. One is a symmetric, one is an antisymmetric. If you've done some quantum, you know exactly what I'm talking about. But you can build many, many of these coherent superpositions. And then you start to do computation with these things. This changes completely the way we see things. How can we use the qubits? The strange thing is that even with one qubit, you already have something which is totally strange, which you cannot get classically. And this is a random number generator. If you generate a qubit in a coherent superposition, like I did here, quantum mechanics is telling us there is absolutely no way you know which way it will be measured. When you measure your qubit, which is a coherent superposition of 0 and 1, it can become a 0 or it could become a 1, and you don't know at all what will happen. There is no way you can predict. That's how you generate, or one way of generating, these random numbers. You can go a bit further and use this qubit to secure communication. If you do that, it's still very simple. You know, we are simple people. We play with single qubits one at a time. So you generate a qubit, but here you make it in 3 possible combinations, okay, as I showed on my graph here. And then the quantum no-cloning theorem is telling you that you cannot duplicate the qubit. It means that if you tell somebody, I prepared one of these 3, but I don't tell you what it is, this person, the bad person, Eve, will not be able to find out, will not be able to duplicate due to no-cloning theorem. And that's the start of quantum key distribution. Basically, it's everything you need to know about quantum to understand quantum key distribution. If we go a bit further, we can take 2 qubits together, for example, and generate entangled states, and we will go towards quantum networks. I will explain a bit. And if you go to many, many qubits, then you go towards a quantum computer. And the quantum computer is basically a new kind of computing machine which can do some of the computation exponentially faster. I'm not going to spend time on that because there have been already talks and there will be others. So we will now focus on quantum communication. Today, quantum communication is really done with single qubits at a time. We play with them and we do a few things. We start with point-to-point QKD and we will go further. Just for the people in the audience who may not really know what we are talking about, I wanted to give you an idea of what is a qubit in terms of photons. So when you see something with your eyes, you receive 1 billion photons per second. Okay, that's the minimum in order to see something. When you want to deal with single photon, a single photon is the light of a candle, which is about 60 kilometers away. Not in Delhi, obviously. In Delhi, it would be probably a bit closer because of the pollution, unfortunately. But you have an idea of the very, very large difference between quantum and non-quantum. It's not like a little bit weaker. It is much, much weaker. And that's why it's not so easy to build a quantum system, to build QKD. Again, you have seen many instances of QKD, so let me be brief about that. Basically, QKD is a way to distribute the photon, measure them, process them, and so on, in such a way that you can be sure that no eavesdropper was there. And at the end of the process, the two users, Alice and Bob, share a key which is proven secret. What's interesting then is that with this key, you can provide security. And the easiest way is simply to add this key to your existing infrastructure. Here, I give you an example with data center communication between a data center and a backup. You already have your encryption system, obviously, with standard classical keys. You can distribute them by RSA today. You will distribute them by post-quantum tomorrow, and so on and so forth. But in any case, if you want higher security, you add a layer of quantum, which means that you add the key, your key which was distributed by quantum, and I think that's important. It was, again, specified by Professor Spiller. It's not a quantum key distribution. It's not a quantum key distribution, sorry. It's a quantum key distribution. What is quantum is a distribution. The key itself is classical, basically. Okay, so here what you do is you generate your key and you input it into your standard system. And this way you improve the security. And of course, the problem was a few years ago to find companies who would accept these keys and integrate them into their systems. We didn't want to reinvent the wheel and build a whole new structure. What we wanted is that people making these encryptors, people making this HSM, hardware security module, or whatever tools they were using for security would accept the keys. What has changed over the last few years is that there are now many, many companies, and a few of them are there. And again, thanks to standardization, we can now insert our key in the system in a totally standard way. So if today you are a manufacturer of, for example, an encryptor, you simply add the ETSI 14 API, and therefore you can then add your quantum, your keys distributed by quantum. Okay? So that's very simple, and you can easily add these keys. Unfortunately, there are limitations. I'm not going to go through all of that because the talk should be short somehow. So because of the main limitation is distance, in order to go longer distances, you need to start building networks. I cannot have a link between Alice and Bob which is too long. We can do today 100, 150 kilometers. But above that, we need to build a network with this trusted node, which we discussed already. And from this, we give the key distribution over longer distances and over much more complex topologies. You build a network, and from this network, you can then distribute keys the way you want. Here I give you a brief example of how we do that. So the lowest layer is the QKD layers, and you see each QKD system is basically linking one Alice to one Bob. And then you have places, the trusted node, the so-called trusted node, where you have many of these Alices and Bobs, and all the keys arrive to these nodes. In order to transmit a key from one end of the network to the other, you go to the layer above, which is called the KMS, Key Management System. And now, if you want to distribute a key from one end to the other, you will use this key management system. You can, for example, create a key at user 1, send it to the key management, and the key management will use the QKD keys to make sure that the key will go from one node to the other, being encrypted by QKD all the way to the end node in a secure way. So you see, you can go from single point to a much larger network, and instead of having to secure the whole network, you have to secure this single point in the network, which are called trusted nodes. We do that at TEC Quantique with our own system. We have two types of system. One is for the backbone, for the main part of the network. We call it a clavis. And for the edge part of the network, you have a system which has slightly less performance instead of dynamic range, and it's called the Cerberus. So now, with this kind of systems, you can basically build a whole network, putting the right elements together and built with these trusted nodes. And we also have the key management system, the above layer, which is already included with the systems. So you see, today, we go from single point to point to a real network with these trusted nodes. This one I can be very brief because my colleague will speak about that tomorrow, I think. So we implemented that already in Korea, and this is, I think, one of the largest projects which is in the world. There are other projects implemented exactly the same idea in Europe, the Euro QciAI initiative, for example. And here the plan is to build a whole pan-European quantum network, which will also include satellites, as we've seen before. And you all know about the big Chinese network, which has been built several years ago already, and which covers something several thousand kilometers. So you see, we have already gone a long way from our simple point-to-point Alice to Bob 100 kilometer to something much more serious. The remaining problem with this is that you got these trusted nodes where the keys will appear because they are classical keys again. So one way to get rid of that is to go to quantum networks. In quantum networks, you generate a quantum state and you want to bring this quantum state all the way to the other end of the network. But now you keep it quantum. I'm not going to discuss all that in details, but I want to give you one of the possible building blocks of a quantum network. It's not the only one, there have been other suggestions, but I think this one is interesting because it looks similar to what is classical as well. So it's based on entangled state and Bell measurement. The only thing you need is to generate an entangled state, and then you see, you take your state you want to transfer, you make a Bell measurement, and once you do the Bell measurement, when you apply your rotation to the other state of the entangled state, you generate again the same state you had initially. Okay? This is really quantum teleportation. So with this basic building block, you see that I can take a state psi, use this entangled state which can be distributed over some distance, and bring it to another state. And of course, then I can do it again and again, and therefore this way I can really build any kind of quantum network. Now, if we look at what is needed here, entangled state, we know how to do them. Bell measurement, we know how to do them, only if we know that the two states arrive together in the measurement. So that's the main difficulty, is that if you generate two quantum states, how do you bring them together at the same time? And that's why you need quantum memories. And that's probably the single thing which we still don't have. I mean, I was happy to learn that one company has already this kind of quantum memories, but I don't think we can buy them today, really. And then you use teleportation, which we also know how to do. So you see, we are not far from these small networks, trusted nodes, and building a real quantum network with no trust. We only need really a quantum memory to build the building block, and the rest is engineering. They say the same about the quantum computer. It's engineering now, but it can take still a while to get finished. But still, the idea is there. And once you got this perfect building block, you can go towards a quantum internet, which is simply a repetition of these things around the world. And hopefully at some stage we will have a worldwide quantum infrastructure which will do whatever we want, basically distributing quantum states from one point to another. And we are still not totally sure of how it will be used, but I think nobody knew how the internet would be used before we built it. So I think that's not a major problem. One last thing I wanted to say about the quantum internet, because I think many people, let's say, are not very precise about that. As I showed before, in order to do this quantum repeater or this, this building block, you absolutely need classical communication. You need communication in order to build a quantum internet, classical communication. So quantum internet will never replace what we have. It will be another structure which will allow you to distribute quantum states. But in order to do that, you also need a regular classical internet. So it's not a replacement, it's an addition. I think that's important to remember that, because some people have been talking about replacing the classical internet by a quantum internet. Of course, it's not at all the case. So basically, as a summary, really is, I would say quantum era is coming, and we need to revamp all our network security. And in order to do that, quantum communication is really required to provide quantum safe security. And we should start today with what we have, quantum key distribution and QKD network. And I showed you that within the near future, we'll have quantum networks, and we will have, I hope, the quantum internet. Thank you.
Thank you, sir. Thank you so much. And now I would request Dr. S.D. Sudarshan, Executive Director of the Center for Development of Advanced Computing, Bangalore, to kindly present memento to the chair. Chairing the session was Shri YGSC Kishore Babu. And now I request Shri Babu to present mementos to our panel. Shri Nagendra Nagaraj. Shri Abdul Kayum. And Dr. Bruno Huttner. Thank you so much. We can have a group photograph if you just step forward here. Yes.